Welcome everyone. Today we are diving into how compiler bridges the gap between human intent and machine logic. We will be focusing on L attribute grammar, the secret sauce that makes a model fast and one pass type checking process. Now, um, look at the declaration int a comma b comma c. As a human, we see int and instantly know it applies to all three variables, but a compiler is a sequential machine. It reads token by token. By the time reaches C, it might have already int, um, forgotten the int, unless we have a specific machine to pass that context sideway through the grammar. Now, let us look like this is where L attribute grammar comes in play. The L stands for left to right, left to right, just as your eyes move across the line of code. This grammar allows us to inject context known as inherited attribute into the system in real time. We don't just wait for the information to bubble up, we push it across. Here are some rules for inherited attribute. Rule number one is an inherited attribute can only depends on symbol strictly on its left. Like let's suppose here we have x2. The x2 can store its values from x1 or from a. Like it should take from top or from left. An inherited attribute can depends on the inherited attributes of its parents. Like it can inherit the properties from its parent or from its siblings, but the sibling should be at its left. It should inherit the properties from the left side only. It can't inherit any properties from x3. Uh, the strict one, this is the one-way process. The strict one-way flow prevents infinite cycle dependencies during tree traversal. Now let us see the differences between um, S attribute and L attribute. Basically, there are two types of attributes. One is S and another one is L. Um, if we have only S attribute grammar, we are strictly uh, bottom up approach. Like we need to follow only bottom up approach. We have to wait for the entire branch of a tree to resolve before we know what's going on. But in L attribute grammar, which gives us the best of both words, then we use synthesized and inherited attributes, allowing for um, mid-fly mid-fly segmentation decision. In type checking, our goal is to bind a type to a name of the s- sorry. In type checking, our goal is to bind a type to a name in the symbol table. In L attribute grammar allows this to happen on the fly. As the compiler encounters each variable name, it already has the type inherited from the left, so it can write to the table immediately. Here, the semantic here this is the main semantic action uh, which bind programming logic. Uh, Now, let us take this production rule. D tends to LT. Here, L inherits its type from T. The L inherits the type resolved from T. It can stores the value from T, like it is storing from left side. And at the same time, we Um, for every identifier in this list, we run a function called add type to update our symbol table. This is how we this symbol table is like inherits the property and adds them into the symbol table immediately. This is how we actually we turn abstract grammar into programming logic. Now let us see the step-by-step process in here. The process starts at bottom left. The compiler sees the word int. It synthesizes the integer type under the integer type upgrade to T node. At this point, the discovery phase is done. The inheritance phase begins. Now, um, now for the magic, like one T type is resolved. The L attribute rule triggers. The context leaps sideways from the left sibling T to right sibling L. Now every child of L is born knowing to its uh, knowing it is an integer. Like every child knows it is an integer because it bounds the properties from left side. It inherited the integer property from T. Now, uh, what if we don't here? Um, L is divided into like L its ID and L1. Now, simultaneously, the type context continues down the chain L1, and the variables here are stored directly into the symbol table. What if we don't use L attribute? We'd be forced into S attribute and bottom-up logic. This compiler would see A and B, but wouldn't know their types yet. It would have to store the entire tree in memory and perform a second costly pass just to link the type. This is a massive waste of memory and time. Here, L attribute architecture is the backbone of one-pass compiling. By evaluating semantics during the initial syntax crawling, we catch we caught a type mismatching error that the moment that they appears. Um, it's the difference between the straight line to execution and a messy tendling phase. Now, let me drive through the uh, key takeaways. First one is left to right design mapping to how we write code. Next one is inherited attributes allow context to leap across the tree. And third one is real-time resolution is the gold standard for modern compilers. This is how we ensure code is safe, valid, and fast. Thank you.